There are other applications that come up from Bernoulli's principle, and one of those is called the magnus effect. So the magnus effect deals with a rotating ball and how it catches the air and what that does. I'm going to first show you a quick video clip of this in action, and then we'll talk about what that looks like and kind of how to predict it.
We're here at the Gordon Dam, and what we're going to do is demonstrate from the very top the effect of spin on a ball. So we're going to get a basketball and drop it from 140 meters up, one without spin and one with spin, and see what happens. All right, you guys good down the bottom?
Sit down here, thank you, we're watching.
Ready? Yeah, so it's crazy, just dropping it with no spin or anything like that, and as you could see, you know, the ball was sort of doing a sway thing, so it wasn't going directly straight. It was pretty hard to predict where it was falling, so that was really cool. Alright, ready? Whoa, look at that go! It's incredible.
Are you one place to get back?
So that's the magnus effect. Now, we should be able to figure this out. If I have a ball like this that is moving to the right, and it's spinning. So think of this as a top-down view. We're going to not worry about things like gravity for a moment. If that's moving to the right, then I have air moving relative to this, to the left. At the bottom, what I have is this point on the bottom of the ball is moving to the left. I also have air moving to the left. So those speeds, they add up. Up here at the top, my air is moving to the left, but the speed of this point on the ball is moving to the right. So those speeds are reduced, which means up here at the top I get a lower speed, and here at the bottom I get a higher speed. In case you're thinking, because I did when I first saw this, in case you're thinking, yeah, but that means that at the top the air and the ball are moving away from each other, so wouldn't that be a higher relative velocity? What we're thinking of instead is this. As the ball rotates, it drags some air with it, like it drags kind of a pocket of air with it. So there is air that wants to move to the left, but that pocket of air moving to the right is working against it. So we get a lower overall speed. At the bottom, the air is trying to move to the left and the ball is helping it along, so we get a higher overall speed. Now, lower speed is going to give us a higher pressure. Higher speed is going to give us lower pressure. So let's look at pressure in purple. We get a high pressure on the top. We get a low pressure on the bottom. And what happens to this ball is it curves this way. Now in this case, it doesn't make a whole lot of sense to look at, because this wants so badly in your head to look like a ball that's just dropping. But again, think of this as a top-down view. So maybe over here you've got the pitcher. That's the top view of the pitcher. Over here you've got a batter. There's their hand. And there's their bat. So they are standing, waiting to hit this ball. Here's the pitcher. They have thrown the ball. And the ball's moving this way. This is how one would throw a curveball. And with a baseball, with a softball, you've got laces on these things. So as this is moving, this ball also has laces, and as you know, that ball is not perfectly spherical. Those laces give it a little bit of, well, bumpiness, right? They give it that extra little bit of dimension. Those are there. You could make this ball without laces. You'd have to make it out of something different, but you could make this ball without laces. Part of the benefit of the laces is that those laces help the ball to grip the air. When those help the ball to grip the air, you can get some real dynamics going. When you throw a knuckleball, you are releasing the ball with little or no spin. Now once it starts to move, once it starts to do anything in the air, it's going to spin a little bit. It's going to start picking up some of these curves, but because that spin is a little bit more erratic, it might curve a little to the right and then more up and then down and go kind of all over the place because those small motions make a difference. Let's look also at a golf ball. Here's a golf ball. A golf ball has all these tiny little divots in it, or dimples, I think they're called on a golf ball. I won't draw them all out. The point of these is the same as the point on the laces on a softball or a baseball. When you hit a golf ball, your golf club is angled something like this. Like the head of your golf club is angled something like that. And what it does is it invokes a backspin on the ball as it's passing through the air. So now I am not looking at a top-down view. Now I'm looking at a direct view, like a side view. As this passes through the air, we get kind of the same thing. We've got air that's trying to move this way. Sort of. It's passing through the air, so relatively that's going on. Up at the top, the ball is moving this way, so it kind of drags the air along, so we get an increased speed here. Down at the bottom, the ball is trying to rotate this way, so it drags against the air, so we get a decreased speed here. Decreased speed is increased pressure, increased speed is decreased pressure. And when we look at the pressure on the ball, then we get a little bit of pressure pushing down, which we can't avoid. We get a lot of bit of pressure pushing up. That generates more lift. So where usually if you hit the ball, the ball is supposed to go in no air at all. It would make a parabola like this, as you know. Because of air resistance, if this ball had no spin or anything like that, we would get something like that that drops off faster. It's an asymmetric parabola. It starts out looking like a parabola, and then it ends up kind of looking like a parabola, but a different parabola. It kind of smushes down. But because of the spin on the ball, because of the magnus effect, we are able to take this thing and maintain that lift for longer and get closer to that result that we would have had with no air at all. Can't play golf very well with no air at all because it's hard to hold your breath for that long. But that's the idea of the magnus effect. We can get movement of a ball that's rotating in the air.